Yes.
which is much better than insertion sort for large data sets, right?
Exactly. It scales much better as the number of elements grows.
Yeah.
But then the book throws another contender into the ring, quicksort.
Another sorting algorithm. I'm starting to feel like I'm at a sorting algorithm competition.
Quicksort is another divide and conquer algorithm,
Okay.
but it works by choosing a pivot element
Good.
and partitioning the array around it, putting everything smaller on one side and everything larger on the other.
So it's like dividing a room full of people based on their height.
Yes.
Everyone taller than the pivot on one side.
Right.
Everyone shorter on the other.
Perfect analogy.
Yeah.
And then you recursively sort those two groups.
Okay.
The catch with quicksort is that the choice of pivot can significantly affect its performance.
Right.
A bad pivot can lead to unbalanced partitions, making it less efficient.
So it's a bit of a gamble. It can be incredibly fast if you choose good pivots,
Right.
but it can also slow down if you consistently choose bad ones.
That's the trade-off. But on
Yeah.
average, quicksort is very efficient.
Yeah.
And we're not done with sorting algorithms yet. The book introduces heapsort,
Okay.
which leverages those heaps we discussed earlier, and radix sort, which sorts elements by their individual digits or characters.
Heap sort.
Yeah.
So we can use a heap to both find the minimum element
Yes.
and sort an entire collection.
Exactly.
That's
And
what-
radix sort is like sorting words in a dictionary.
Gotcha.
You first sort by the first letter, then the second, and so on.
Yeah.
It can be very efficient for certain types of data.
Okay, my head is spinning with all these sorting algorithms.
I know there are a lot.
Is there a cheat sheet for choosing the best one?
Unfortunately, there's no one-size-fits-all answer.
Right.
The best choice depends on the size of the data set,
Okay.
the type of data, and your performance requirements. It's about understanding the trade-offs and making informed decisions.
And the book equips us with the knowledge to do just that.
It does.
It also talks about external sorting, which is for dealing with data that's too large to fit in memory.
Yeah,
Right.
that's right.
Yeah.
External sorting is about working with data on disk, which is much slower than working with data in memory.
Right.
It requires clever techniques to minimize those expensive disk accesses.
So it's like having to sort a library full of books.
Oh, yeah.
You can't just bring them all to your desk at once.
Exactly. You need a strategy for moving the books around efficiently.
Yeah,
Okay, we've thoroughly sorted out sorting algorithms.
I have.
Now let's move on to a data structure I haven't encountered before. Disjoint sets.
Disjoint sets?
Yeah, they're all about representing groups of elements
Right.
that are partitioned into distinct, non-overlapping sets.
Okay.
Imagine a school with different clubs. Each student can only belong to one club at a time.
So it's like a way of tracking group memberships.
Exactly. Disjoint sets let you perform operations like union,
Okay.
which merges two groups together,
Right.
and find which determines which group an element belongs to.
That sounds like it could be useful in a lot of scenarios.
Yeah, absolutely.
Network connectivity, image segmentation, social network analysis, anywhere you're dealing with groups and memberships.
Absolutely. And the book presents a really elegant data structure for representing disjoint sets. The disjoint set forest.
A forest of sets. Now I'm really picturing trees.
Well, it's a collection of trees
So,
where each tree represents a disjoint set,
right.
and the root of each tree acts as the name of the set.
Okay, so it's like a forest of family trees where each tree represents a different family.
That's a good visualization.
Yeah.
And the book explains how to perform union and find operations efficiently using this tree-based representation.
Okay.
It even introduces some optimizations like path compression and union by rank, which help keep things running smoothly even as the number of elements grows.
So again, it's about understanding the trade-offs and making the most of the data structure.
Exactly. Now, get ready to enter a vast and interconnected world.
Okay.
We're moving on to graphs.
Graphs.
Yeah.
Like the ones we use to plot data in math class.
They're related, but much broader in computer science.
Okay.
Graphs are a powerful way to represent relationships and connections between things.
Right.
Think social networks, roadmaps, computer networks, anything where you have entities and links between them.
So the classic image of a network of dots connected by lines.
That's it. The dots are called vertices or nodes, and the lines are edges.
Right.
And the book explains different types of graphs, like directed and undirected graphs,
Okay.
weighted and unweighted graphs, each capturing different kinds of relationships.
So roadmap with one-way streets would be a directed graph.
Yes.
Because the connection goes only one way.
Right.
Whereas a map with two-way streets would be undirected.
You got it.
Yeah.
And a map where each road has a distance associated with it would be a weighted graph,
Okay.
while a map showing only connectivity would be unweighted.
Okay, I'm starting to see how powerful graphs are for modeling real-world relationships.
Absolutely.
And the book dives into a whole bunch of graph algorithms.
It does, yeah.
Shortest path, minimum spanning tree, graph traversal.
Exactly. Think about finding the fastest route on a map.
Mm-hmm.
That's a shortest path problem.
Right.
Or connecting a network of computers with the least amount of cable.
Yeah.
That's a minimum spanning tree problem.
Okay.
And graph traversal algorithms let you systematically visit every node in a graph,
Right.
like exploring a maze.
So there's a whole toolkit of algorithms for solving different kinds of problems on graphs.
Absolutely.
Okay.
And the book does a great job of introducing the classics.
Yeah.
Dijkstra's algorithm for shortest paths,
Mm-hmm.
Prim's and Kruskal's algorithms for minimum spanning trees,
Right.
depth-first search and breadth-first search for graph traversal. It's like having the Swiss Army knife for navigating the world of graphs.
Okay, this is getting pretty deep. The book even touches on NP completeness,
Oh, yeah.
which sounds a bit
The
intimidating.
NP completeness is a concept in computer science that deals with the difficulty of solving problems.
Right.
NP complete problems are a class of problems that are believed to be very hard,
Right.
meaning we don't have any efficient algorithms to solve them for all cases.
So if we hit an NP complete problem, are we just stuck?
Not necessarily. There are strategies like approximation algorithms,
Okay.
which try to find good enough solutions,
Right.
and heuristic algorithms,
Mm-hmm.
which use rules of thumb or educated guesses.
Okay.
It's about being aware of the complexity and having strategies for dealing with it.
Okay, so graphs and NP completeness, we're really getting into the theoretical side of computer science now.
Well, the theory underpins the practice.
Yeah.
And the book does a fantastic job of making these complex ideas accessible.
So we've explored graphs and their algorithms,
have.
and even dipped our toes into NP completeness.
Yes.
What's next in our data structures and algorithms adventure? Okay, so we've explored this vast landscape of data structures and algorithms, from lists and trees to graphs, and even touched on the challenge of NP completeness. What's next on our journey?
Well, hold on to your hats, because Chapter 10 takes us into the realm of advanced algorithm design techniques. We're talking about strategies that go beyond the basics, like greedy algorithms, divide and conquer, dynamic programming, and even randomized algorithms.
Wow, that sounds like we're leveling up our coding skills.
Absolutely. These techniques are like the secret weapons in a programmer's arsenal.
Okay.
They help us tackle complex problems more efficiently and elegantly.
Let's start with greedy algorithms.
Okay.
We've already encountered them with minimum spanning trees. What other problems can they solve?
Greedy algorithms are all about making the best choice at each step without worrying about the long-term consequences. Think of it like picking the juiciest strawberries at the top of the basket. You're
Yeah.
not planning ahead, just grabbing the best option at that moment.
Sounds a bit impulsive,
Yeah,
but I guess it can be effective in some cases.
you're right. It doesn't always lead to the absolute best solution overall,
Right.
but it can often provide good solutions quickly.
Okay.
Greedy algorithms are used in things like Huffman coding for data compression, job scheduling for optimizing task execution, and even finding the shortest path in a graph.
Huffman coding, that rings a bell. It's how we compress files to make them smaller, right?
Exactly. It uses a greedy approach to assign shorter codes to more frequent characters, resulting in a smaller overall file size.
So it's like packing a suitcase.
Yeah,
You put the bulky items in first, and then fit the smaller things around them.
that's a great analogy. Now let's talk about divide and conquer, which we've already seen with mergesort and quicksort. What other tricks can it pull off?
Divide and conquer always reminds me of that famous Julius Caesar quote. Divide et impera, divide and rule.
Yeah.
It's about breaking a problem into smaller pieces, solving those, and then combining the solutions.
It's a powerful strategy. Besides sorting, divide and conquer can be used for things like finding the closest pair of points in a set, multiplying matrices efficiently, and even solving those mind-bending recurrence relations from math class.
So it's a general problem-solving framework that can be applied to many different domains.
Absolutely. And then there's dynamic programming, which takes a slightly different approach.
Okay.
Instead of breaking a problem into completely independent subproblems, it breaks it down into overlapping subproblems and stores the solutions to those subproblems to avoid redundant calculations.
So it's like building a reference guide as you go along, so you don't have to solve the same problem multiple times.
That's a great way to put it. Dynamic programming is particularly useful for optimization problems, like the classic knapsack problem, where you're trying to maximize the value of items you can fit in a knapsack with a limited weight capacity.
That sounds like a real-life dilemma. And dynamic programming helps us find the best combination of items without having to try every single possibility.
Exactly. It's a clever technique that can save us a lot of computational effort. Now, prepare yourself for a bit of a mind-bending concept,
Mhm.
randomized algorithm.
Randomized algorithms.
Yeah.
So we're introducing randomness into the mix.
Yeah.
Doesn't that make things less predictable?
You're right. Randomized algorithms don't always produce the same result for the same input,
Right.
but that's not necessarily a bad thing.
Okay.
Sometimes embracing randomness can lead to simpler, more efficient solutions, especially when dealing with problems where deterministic algorithms struggle.
Okay. I'm intrigued. What are some examples of these randomized algorithms in action?
The book talks about randomized quicksort, which, as the name suggests, uses randomness to choose the pivot element. This helps to avoid those worst-case scenarios where quicksort can slow down significantly.
So it's like shuffling a deck of cards before sorting them. You're making it more likely that the cards will be distributed evenly.
That's a great way to think about it. And then there are Monte Carlo algorithms, which are like rolling dice to get an approximate answer. They might not always be perfectly accurate, but they can be much faster than trying to find the exact solution.
So it's a trade-off between accuracy and speed.
Exactly. And then there are Las Vegas algorithms, which always produce the correct answer but might take a variable amount of time, kind of like playing the lottery. You're guaranteed to win eventually, but you don't know how many tickets you'll have to buy.
Okay, I'm starting to see how randomness can be a powerful tool in algorithm design.
Yeah.
It's not just about being precise. Sometimes it's about finding a balance between efficiency, accuracy, and simplicity.
Exactly. Now, before we move on, there's one more technique that's worth mentioning. Backtracking algorithms.
Backtracking, like when you realize you've taken a wrong turn and have to retrace your steps.
That's a great analogy. Backtracking is a problem-solving technique where you try different solutions incrementally and backtrack when you hit a dead end. It's like exploring a maze. You try one path, and if it leads to a wall, you go back and try a different one.
So it's a way of systematically exploring different possibilities until you find a solution.
Exactly. Backtracking is particularly useful for constraint satisfaction problems, like the classic eight queens puzzle, where you have to place eight queens on a chessboard so that no two queens can attack each other.
I remember trying that puzzle as a kid.
Yeah,
Surprisingly tricky.
it is. And backtracking provides an elegant way to solve it. You place one queen at a time, and if you reach a point where no more queens can be placed safely, you backtrack and try a different position.
Okay, backtracking sounds like a powerful technique for solving those find all possible solutions kind of problems.
It definitely is, and the book does a fantastic job of illustrating how it works. Now, let's take a step back and talk about amortized analysis, which is a way of analyzing the performance of algorithms over a sequence of operations rather than focusing on the worst case performance of a single operation.
So it's like looking at the big picture instead of just focusing on isolated events.
Exactly. Amortized analysis helps us understand the true cost of algorithms, especially when certain operations are performed more frequently than others.
Okay, can you give me an example?
Think about dynamic arrays, which are arrays that can grow in size automatically when they get full.
Right.
Inserting an element into a dynamic array is usually a very fast operation.
Yeah.
But occasionally, when the array is full, you need to resize it, which can be quite slow. Amortized analysis tells us that even though resizing is expensive, it happens so infrequently that the average cost of insertion remains very low.
So it's like paying a small monthly fee for a service instead of a large upfront cost.
That's a good analogy. The book also discusses how amortized analysis applies to data structures like binomial queues and Fibonacci heaps, which we've already encountered. They both use clever techniques to ensure that their average performance is excellent, even if individual operations might occasionally take a bit longer.
Okay, I'm starting to see the value of amortized analysis.
Yeah.
It's about understanding the long-term cost of algorithms, not just focusing on isolated spikes in performance.
Exactly. Now, let's move on to a special type of binary search tree called a splay tree.
Okay.
These trees are self-adjusting, meaning they reorganize themselves to bring frequently accessed nodes closer to the root.
So it's like having a bookshelf that automatically rearranges itself so that the books you use most often are always within easy reach.
That's a fantastic analogy. Splay trees are fascinating because they adapt to usage patterns, making frequently accessed data faster to retrieve.
And the book explains how this splaying operation works, involving a series of tree rotations to move the access node towards the root.
It's quite elegant. Splay trees have some interesting properties. They offer good amortized performance, which means that the average cost of operations remains low, even though individual operations might occasionally be a bit more expensive.
So they're a good choice when we have unpredictable access patterns and want to optimize for the most frequent operations.
Exactly. Now, get ready for the grand finale. Chapter 12 introduces us to some advanced data structures and implementation techniques that push the boundaries of what we can do with algorithms.
I'm ready for the challenge. What's in store for us?
The chapter starts with a deeper dive into splaying, discussing a non-recursive implementation called top-down splaying, which can be more efficient in certain scenarios. Then it introduces us to trees, which are a fascinating hybrid of binary search trees and heaps.
Heaps. So we're combining the ordered structure of binary search trees with the priority-based structure of heaps.
Exactly. Each node in a tree has both a key, like in a binary search tree, and a priority, like in a heap. The tree is structured in a way that satisfies both the binary search tree property and the heap property simultaneously.
Okay, that sounds a bit mind-bending. What are trees good for?
They have a variety of applications, including implementing randomized search trees, maintaining sorted sets efficiently, and even simulating things like rope splicing, which is used for manipulating long strings of text.
Rope splicing.
Yeah,
That sounds intriguing.
it's like taking a physical process and representing it digitally.
Yeah.
And trees provide a surprisingly elegant way to do it. Now let's talk about data structures that are specifically designed for working with strings, suffix arrays, and suffix trees.
Strings. So now we're dealing with text, not just numbers.
That's right. Suffix arrays and suffix trees are incredibly powerful data structures that allow us to efficiently search for patterns within a string. Imagine you're building a search engine and you want to find all the web pages that contain a specific word or phrase.
That's a real-world example. How do these structures help with that?
Suffix trees essentially create an index of all the suffixes of a string.
Okay.
This allows you to quickly find all the occurrences of a particular pattern within that string. They're incredibly efficient for pattern matching, which is essential for tasks like text searching, DNA sequence analysis, and plagiarism detection.
Wow, that's amazing. It's like having a super-powered search function that can instantly find any pattern within a huge text document.
Exactly. And finally, we're introduced to KD trees, which are a generalization of binary search trees to higher dimensions.
Higher dimensions. So we're moving beyond the familiar two-dimensional world.
That's right. KD trees allow us to work with data points that have multiple attributes, like points in a three-dimensional space or even data with dozens of attributes. Imagine you're building a system for recommending nearby restaurants based on your location and cuisine preferences.
That sounds like a real-world application. How do KD trees help with that?
KD trees partition the space into regions, making it very efficient to search for points within a specific range or to find the nearest neighbors of a given point. They're used in all sorts of applications, from computer graphics and image processing to database indexing and machine learning.
Wow, we've really covered a lot of ground in this deep dive. From basic data structures like lists and stacks to advanced algorithms and techniques like dynamic programming and KD trees, we've explored a whole universe of tools for organizing and processing data efficiently.
This book is truly a treasure trove of knowledge for anyone who wants to master the art of computer science.
I couldn't agree more. It's been an incredible journey, and I feel like we've only scratched the surface of what this book has to offer.
And that's the beauty of it. There's always more to learn and explore in the world of data structures and algorithms.
So to our listeners, if you're fascinated by the power of algorithms, if you want to write code that's not just functional, but elegant and efficient, or if you're just curious about the inner workings of the digital world, I highly recommend diving into this book. It's a challenge, but it's a rewarding one.
Absolutely. It's a journey that will transform the way you think about data and problem solving.
So thank you for joining us on this deep dive into the world of data structures and algorithm analysis in C++ Sign. We hope you've enjoyed the journey, and we encourage you to keep exploring the fascinating world of computer science.